So our next speaker is Tuomas, Hakoniemi, and he will talk about our CNF instances for ideal proof systems.
Thank you. Thank you, and thank you for the organizers for letting me speak, and thank you for Susanna and Kilian for a very nice introduction before this talk. So this is also a proof complexity talk about algebraic proof complexity, and I will start by repeating some of the things that Susanna and Kilian already talked about. Okay, but so just to remind everybody, so what's a propositional proof complexity about? So we are interested in lower bounds for propositional proof systems, proving size lower bounds for different systems. And the basic question is, of course, what's the size of the smallest refutation of a CNF for some propositional proof system P? And Susanna gave a kind of introduction to a current state of art there. So some of the examples are resolution or the Fred systems, which are the so-called text style proof systems that you would find in any logic text, basically. And for this talk, an important open frontier is proof systems that can do parity reasoning, which are the rest parity that was mentioned by Susanna also, and AC null parity Friday. Okay. So like both Susanna and Kilian already told you, the algebraic proof systems were introduced with the explicit hope to proving these lower bounds for AC null parity Friday by algebraic means. So here we do a slight switch in the setup usually. So we are playing with some kind of an expanded playing field usually. So rather than just looking at CNFs, we can look at general unsatisfiable sets of polynomial equations. Usually we ask them to be unsatisfiable over the Boolean values. Okay, so this is both a blessing and a curse for us. So a pro is, of course, more lower bounds, but the downside is that these might not be comparable to lower bounds in propositional proof complexity. So if you prove lower bound for some more general set of polynomial equations, this might not say anything really about the proposition of the complexity. Okay, so the basic proof system is introduced already is the Nutan as proofs, right? Introduced by Beam, Impagliazzo, Grochow, Pitassi, right? To prove complexity, where the proof is given by a sequence of these weights. I call these polynomial weights, so that this weighted sum is equal to 1. And I'm using this equivalence sign to mean equal modulo multilinearization, so equal modulo Boolean axioms. Okay. So I realize that I have slightly different years than the previous talk had, but these are the journal dates, and I think they had the conference years. Okay. So this talk is really about this IPS Lin, which is basically a proof system that measures the size of the proof by the algebraic surface size of these weights. So the subscript lim here means that we're actually looking at this kind of a Nutan refutation. So IPS in more generality will allow you to represent even this sum more succinctly if you want, but this is the system we are going to consider here. Okay. And the main motivation here is, of course, that even constant depth subsystem here simulates this AC not parity failure. So maybe proving lower bounds for constant depth IPS lim for a CNF, you get this lower bounds for AC not parity. Okay, so a small selection of previous work on this unconditional lower bounds. So several unconditional lower bounds are known for different classes of algebraic circuits. So, for example, for ROABPs, sums of ROABPs, multilinear formulas and formulas, and then constant depth circuits. So the paper that kind of started this line of work on this unconditional lower bound is this FSTW, Fox, Hilka, Tzameret and Iddo, where they proved some lower bounds for the ROABPs and multilinear formulas, and introduced the two basic methods to prove these lower bounds that are basically used elsewhere in these papers. Okay, but there's a common problem here, which is that the hard instances are not CNFs. So for many of these, they are some form of a subset sum principle. So you have some kind of a sum of polynomials. You claim it's equal to some field element, and it cannot be equal to that over zero values, and then you want to refute that. Okay. Yes. So coming to our main contribution here is that we show that there's a CNF formula that requires ROABP IPS link refutations of width at least to the n to the omega 1. Okay, so just a quick reminder, what is this ROABP, right? It's a ROABP is compute polynomials. So it consists of a sequence of matrices of univariate polynomials, right? And you basically compute, let's say, the top left entry of this product, right? So a few comments about these results. These are stronger than the sparsity lower bounds that Susanna was talking about. This theorem works over any field and over any representation of these Boolean values that was discussed in the previous talk. And the last point is true because this measure is invariant under these shifts of the basis.
You didn't say what is the measure? Width.
Oh, the width. Oh, yes, thank you. So the width is basically the maximal dimension of a matrix here. Okay. So how do we do this? So this model comes with some ordering of the variables in which you multiply the matrices, right? So there's basically a two-step proof. First for some fixed variable ordering, and then to a arbitrary variable ordering. So the fixed variable ordering is via so-called monotone feasible interpolation with monotone span theorems, and the arbitrary variable ordering is a gadget construction on top of that. So in this talk I will talk about the first one, and if you're interested in the second one, come and ask. Okay, so let's take a breather. Any questions? Good time to have a sip of coffee. Okay. So So yeah, let's continue. So what's this feasible interpolation? So it's not. I think I need to say to this audience that it's not interpolation in the sense of polynomial interpolation, but it's interpolation in the sense of Greg's interpolation in logic. So this is a framework introduced by Grochow that basically translates circuit size lower bounds to proof size lower bounds. And how do you do this? It's basically you consider this kind of a split CNF. So you have a conjunction of two CNFs that share some common variables, right? Some split unsatisfiable CNF should be there. So then you call this kind of function that outputs basically tells outputs 0 if the first one is satisfiable on an assignment to the common variables, and 1 if the second one is satisfiable. Because this is an unsatisfiable, this is a well-defined function. Both cannot be satisfiable at the same time. So you should think about this basically. The A and B, they are defined into NP sets, and you're asking about the functions separating those NP sets. Right. And feasible interpolation is this idea that, okay, can we upper bound basically the complexity of computing this interpolant by the proof complexity. So we say that a proof system has feasible interpolation if some kind of refutation of this formula can be in some way turned into a like an efficient algorithm computing the interpolant, right? And this framework has been used to prove, for example, lower bounds in resolution and for cutting planes. So here, for resolution, the circuit class you're interested in is monotone Boolean circuits, and in the cutting planes it's monotone real circuits, right? But this property is, in a sense, indication of some kind of weakness in the proof system. So under some crypto assumptions, no strong proof system can have feasible interpolation. So basically, if you'd had feasible interpolation with respect to some circuit class, then that circuit class could break RSA or Diffie-Hellman. Okay. So how would you go about basically computing this kind of an interpolant? And one way is to do this via proof search. So simply on an input to the common variables, just search for a refutation of one of the conjuncts. So if you have found that, then well, you have found a refutation. It's unsatisfiable. You can output safely the one because because you are only required to output 0 if this A is satisfiable. And on the other hand, if you cannot find it, then the other formula is unsatisfiable and you can safely output 0. And why is this other formula unsatisfiable? Well, if it was satisfiable, then your given refutation with this satisfying assignment would reduce down to a refutation of the first formula. So you should have found it. So there's a lot of counterfactual kind of inferences here going on. Okay, but let me see. So in some sense, the main message is that if you can limit somehow now the search space, then you can get a feasible interpolation algorithm for this. So let me first go through a very simple example, or more simple example, is this degree-bounded Nutan refutations. So say you have this degree D refutation of this split formula, looking like this, right? And an assignment to the common variables, right? So now, very simple, but the key observation here is, okay, if the right-hand side was satisfiable, then plugging in that satisfying assignment would reduce this down to a degree D refutation of the left-hand side. So it suffices to only look for a degree D refutations of the left-hand side and answer according whether you find such a refutation. And this is, doable easily by a small linear program, basically, if you have a fixed degree bound here. And in a work of Budlak and Skal, they show that this is actually can be done by this proof search can be done by a span program of relative size also. And this result of Budlak and Skal is the kind of a result that will follow here also. Okay. So what about ROIB IPS Lim? Okay. So basically, we want to find similarly some kind of a small space of polynomials where we can find these refutations in order to interpolate this proof system. So refutation looks like this again. Now the weights, these QCs are computed by with W ROIBPs, right? So here's the key assumption about the ordering of variables. This is the fixed ordering case. We assume that the order is such that the x variables are queried before any other variable. And this gives us this key property that, okay, we can actually write each of these weights as this kind of a small sum of a polynomial only in the x variables times a polynomial in the rest of the variables. Right. So requires to just search for proofs in this small dimensional space spanned by these polynomials. Right? Okay, and so the other part of the statement was that we can do this search by monotone span programs. So I will introduce these next. So a span program, it's a model of computation introduced by Kashmir Bigdaston, right? So it consists of a matrix where you have rows labeled by your literals in some Boolean variables, right? And then a target vector. And how does this compute a Boolean function? So you output on an assignment to the literals, you output 1 if and only if the target vector is in the span of the rows selected by this assignment. So this assignment satisfies some of the literals assigned to each row, and you just take those rows with a satisfied literal. Okay. And monotone span program is a span program where the labels are only positive literals. And for this model, we actually have exponential lower bounds by first work of Robert, Pitassi, Rosman and Cook, and then that was for reals, and then Pitassi and Robert for any field. And so how do you do this proof search with the span program? This is kind of simple, actually very simple. But here we have to do this again, a small assumption about the CNF. So we assume that the clauses in this this first formula contain at most one z variable, and that z variable, if it appears, is negative. So this is our kind of monotonicity assumption that allows us to use monotone span programs to search for the proof. Okay. So this is because now the translation of each of these clauses into polynomials, this translation, Susanna had it on one slide. The translation of any of these clauses then looks like just a z variables times some polynomial only in the x variables, or simply a polynomial in the x variables. So now the proof search is kind of a simple. It's just searching for a null-Stellensatz refutation where the weights are from this small dimensional space, right? So for each axiom that's of the form ZP, well, you include it in your search if Z is satisfied by your assignment. Otherwise, you don't. And if it doesn't include this Z, then you just include it in your search. Have it labeled with 1. And the target vector is, of course, simply the constant polynomial 1. This is what we are looking for in the null-Stellensatz refutation. Okay. So, and what's the hard instance here? It comes from these exponential lower bounds for the span programs. But there's one key property here is that there's an exponential lower bound for a function that's computable in polynomial time. And because it's a polynomial time, we can define the split formula that one side states that, okay, the assignment to the common variables is a 0 input of this function. And the other side states that, no, it's actually a 1 input of the function. So then any interpolant of this formula is exactly the gen function. So we get the exponential lower bounds for these ROABB IPS refutations in this fixed ordering from the lower bounds on monotone span programs. Okay. So, yeah. So wrap up, what we proved is CNF lower bounds for ROABB IPS lim via feasible interpolation, and some open questions. So first, can we do slightly stronger lower bounds? We had this 2 to the n to the omega 1 lower bounds. Can we do 2 to the omega n? And this is related to the other question about other models, especially this multilinear formula IPS. So if you can prove, basically, if you can prove very strong lower bounds in the ROABB case, that will give you multilinear formula IPS lower bounds. And then maybe some other more explicit hard instances. This is kind of a not so natural hard instance at the moment. So thank you for your attention.
Questions?
Just a note. Just a quick note about the last open question. Are there more explicit hard instances? But so that's what we note in the write-up. That the idea of algebraic tiling suggested by Dima Sokolov solves this. Every instance which is hard for Nutan's degree can be transformed explicitly into a hard instance with a lifting in this model.
Yeah, but that would still include some kind of a lifting, maybe. So
Oh, so it's not
Yeah.
explicit in your sense. Okay.
Anyone else? It's time, Tuomas, I think.